Let's talk about heat engines. What is a heat engine? A heat engine is basically any device that converts heat to work. Typically, they're getting heat from some high temperature source. So it could be, solar, oil, nuclear reactor, whatever. And then it's taking that energy and it converts part of that heat into work. Typically, it's some kind of like rotating shaft work, right? You generate steam and turn a turbine, and then they reject the remaining waste heat to a low temperature sink, right? So something like a river or the atmosphere, lake, whatever, ocean. And they operate on a cycle. So there's some kind of cyclic nature to the process. So remember now, you can take work and you can convert it into heat directly, but you can't do the reverse, right? You can't just apply heat and turn it into work in a system like this. You need some kind of cycle to do that with. And so this is where we're talking about heat engines and other cyclic devices. There's typically some kind of fluid, which is called the working fluid. And that working fluid is what actually takes and does the heat transfer, right? That's the one transferring the heat from the high temperature source into the process and then out of the process to the low temperature sink. All right, this is a schematic of a steam power plant. And I just want to go through, you have a boiler that generates steam, which turns the turbine. The remaining steam, the cooler steam and the condensate goes to condenser, which cools it off even further. And then it gets pumped back to the boiler where it's heated up again. So this is a typical steam power plant cycle. Notice there's a few terms of interest here. Q in, this is the amount of heat that's supplied to the steam from a high temperature source, like a furnace or some kind of burner or a nuclear power plant. Q out is the amount of heat that you reject from this cycle to the low temperature sink. W out, that's the work you get out of the cycle. And W in is the amount of work you have to put into the cycle. And this goes into recirculating the fluid, basically recompressing it to put it to the boiler. And you can write these equations. Your net work is work out minus work in. And your net work out is also the heat in minus the heat out. That's the equivalent energy that you're getting in net work. And that's for a cycle. Okay, so a heat engine, notice the term I have, the net work out is work out minus work in. Remember, we had to take some of that work and consume it internally, right? You had work in that went into the heat engine, and you got work out of the heat engine. So some of that work is consumed to keep it operating. Let's talk about thermal efficiency. Thermal efficiency is basically the net work output over the total heat input, right? So you got work out of your process by putting heat in. And the thermal efficiency is denoted by this eta, the Greek letter eta sub th. And you can see it's written net work out over Q in. Let's see, and remember, the net work out is Q in minus Q out, so you can substitute in and rearrange algebraically and get an expression for efficiency, thermal efficiency, that's a function just of the heat in and out of the system. So if you know the heat input and you know the heat output, you can figure out what the thermal efficiency of the heat engine is. And that's what thermal efficiency is, the fraction of the heat that's basically converted into work. And this is what it looks like. You can see here there's two different heat engines, heat engine 1 and heat engine 2. Notice they're both using the same source, right? They're both getting 100 kilojoules of heat. Heat engine 1 is putting out 20 kilojoules of work. Heat engine 2 is putting out 30 kilojoules of work. If we look at the waste heat, over here we're dumping 80 kilojoules. Over here we're dumping 70 kilojoules, right? So just looking at this process, you can see intuitively, okay, we're dumping more waste heat from process 1 than process 2. We're converting more heat into work over here than we are over here. And the thermal efficiency is a measure of that, right? Thermal efficiency of system 1 is basically 1 minus Q out over Q in. So 80 divided by 100, 1 minus that. And then the same thing over here, 1 minus 70 over 100. So the thermal efficiency here is 20%, here it's 30%. So this tells you this process is more efficient based on the heat energy in and out. All right, here's a schematic of a heat engine. We've already seen you've got a high temperature reservoir. You supply a certain amount of heat into the process. You get a certain amount of work out, and you have to dump a certain amount of heat to the low temperature reservoir. And inside here is the process, right? You can notice the little turbine, the pump, the two heat exchangers. So QH is the magnitude of heat transfer between the high temperature medium and the cyclic device at this temperature, T hot. QL is basically the quantity or the magnitude of heat transfer between the cyclic device and the low temperature reservoir, and this is denoted by TL, right? So these are constant temperature reservoirs for this specific situation. So because the net work out is QH minus QL, right, we can rearrange this again. We can write this efficiency, thermal efficiency, we got this on the last page, 1 minus QL over QH. And here we have, again, the same equation. Net work out is QH minus QL. I'm just showing this for... So now here we have some numbers associated with these hot and basically heat rejection, or heat input and heat rejection, right? We've got 100 megajoules in, we get 55 megajoules of work out, and we get 45 megajoules of heat dumped to the atmosphere. And the point is here that we can calculate this efficiency based on these numbers, and even the most efficient heat engines reject almost 1/2 of the energy they receive as waste heat. This is just a fundamental problem in application, right? When you're trying to, make a heat engine, that you wind up wasting almost half the energy that you get as waste heat. All right, so could we save Q out, right? How do we reduce the heat lost out of the process? And let's think about this. In reality, right, a steam power plant, you have some kind of condenser where you reject heat to some kind of large reservoir, like a river, a lake, or the atmosphere. And the question arises, can we just take the condenser out and save all that waste heat, right? Why not just reuse it? But the problem is that no, you have to reject that heat, that waste heat, to some external reservoir in order to complete the cycle. And let's see, yeah, every heat engine must waste some energy by transferring it to a low temperature reservoir to complete the cycle, even under ideal conditions. So we'll talk about ideal cycles later. But this is sort of a fundamental rule, right? And let's look at what a cycle is in a heat engine. So imagine we have a piston with a load on top of it, and it's got some gas trapped in this chamber, and the piston moves between two stops. So we take this piston and we first put it in contact with a heat reservoir at 100 degrees C, and it transfers heat to the gas, right? So we put 100 kilojoules of heat in. And then by lifting this load, we perform 15 kilojoules of work, right? But now we have in here, we've got gas at 90 degrees C. How do we complete the cycle? Well, somehow we've got to cool this gas down, right? So we put that in contact with a cool reservoir, and we cool this piston back down. Maybe you've taken the load off, but the point is that in order to complete a cycle, you need to be able to go between. This is a very simple, basic example, but it represents a cycle. So you have to reject some heat to some kind of sink. All right. You can also take the rate of change, the time rate of change of these things, right? So you can take the work divided by time and heat divided by time, and you can get power production, right? So this is the net power. If you know you're transferring heat at 80 megawatts and you're rejecting heat at 50 megawatts, well, your net power is 30 megawatts, right? And you can write also efficiency with respect to those rates, right? As long as it's per some unit time, per work, joules per second, kilojoules per second, megajoules per second. So you got 30 megawatts over 80 megawatts. This gives you an efficiency of 37.5 for this process. All right. Finally, let's look at the Kelvin-Planck statement that's applicable to heat engines. Basically, what this statement says, Kelvin and Planck came up with the thermodynamic principles that it's impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. And basically what this is saying is no heat engine can have 100% thermal efficiency. You have to have a working fluid that exchanges heat with the environment as well as the heat source, in this case typically a furnace. So this is not due to friction or other dissipation. It's a limitation, and it applies to actual heat engines or idealized heat engines. So this is basically a rule that Kelvin and Planck came up with. This is what a heat engine would look like that violates the Kelvin-Planck statement, right? You've got a thermal reservoir. You're transferring 100 kilowatts of heat, and you're getting 100 kilowatts of work out, and there's no heat transfer to the environment. This is an impossibility. This is a violation of the Kelvin-Planck statement. You need to dump heat to some reservoir.